Hello everyone, my name is Dmitrii Ivashchenko, and I'm a software engineer at my.games. In this talk, we'll look at the differences between WebGL and soon-to-be-released WebGPU, and learn how to prepare your projects for this transition. Let's begin by exploring the timeline of WebGL and WebGPU, as well as the current state of the WebGPU. WebGL, similar to other technologies, has a history that dates back to the past. The desktop version of OpenGL debuted way back in 1993. In 2011, WebGL 1.0 was released as the first stable version of WebGL. It was based on OpenGL 2.0, which was introduced in 2007. This release allowed web developers to incorporate 2D graphics into web browsers without requiring any extra plugins. In 2017, a new version of WebGL was introduced, called WebGL 2.0. This version was released 6 years after the initial version and was based on OpenGL 3.0, which was released in 2012. WebGL 2.0 came with several improvements and new features, making it even more capable of producing powerful 3D graphics on the web. Lately, there has been a growing interest in new graphics API that offer developers more control and flexibility, and three notable APIs here are Vulkan, Direct3D 12, and Metal. Together, these three APIs create a foundation for WebGPU. Vulkan, developed by the Kronos Group, is a cross-platform API that provides developers with lower-level access to the graphics resource hardware. This allows for high-performance applications with better control over graphics hardware. Direct3D 12, created by Microsoft, is exclusively for Windows and Xbox and offers developers deeper control over graphics resources. Metal, an exclusive API for Apple devices, was designed by Apple with maximum performance in mind on their hardware. WebGPU has been making significant progress lately. It's expanded to platforms like Mac, Windows, and Chrome OS, and available in Chrome 130 and Edge 130 versions. Linux and Android support is expected to be added soon. There are several engines that either support or are experimenting with WebGPU. Babylon.js fully supports WebGPU, while Three.js currently has experimental support. PlayCanvas is still in development, but its future looks promising. Unity made an announcement of early and experimental WebGPU support in alpha version 2023.2, and CodeCreator 3.6.2 officially supports WebGPU. And finally, Construct is currently only supported in Chrome version 130 or later on Windows, macOS, and Chrome OS machines. Taking this into consideration, it seems like a wise move to start transitioning towards WebGPU, or at least preparing projects for a future transition. Let's take a closer look at some of the core pieces of the API. This won't be comprehensive, but we'll touch on all the most important bits. The GPU adapter is a pivotal component. Adapters represent the GPUs the device can be accessed. This can be even software-based, like Swift Shader, and typically it returns one adapter at a time. However, you can specify an adapter based on certain criteria, like power performance, low power, and it provides a snapshot of the GPU specifications, such as vendor NVIDIA architecture tuning, and furthermore, it outlines the features and limits applicable to the GPU device. The GPU device plays a central role. It serves as a main interface for the API. This component is responsible for creating resources such as textures, buffers, and pipelines. It comes equipped with a GPU queue to carry out commands, and functionally it's quite akin to WebGL rendering contexts. WebGL extensions are roughly equivalent to those in WebGPU. However, they are not universally supported across all systems. Each adapter provides a list of available extensions. To activate them, they must be specified when requesting the device. There are numerical constraints on GPU capabilities. A baseline exists that every WebGPU implementation must meet. The adapter indicates the actual limits of the system. By default, only these limits are active unless specified during the device request. WebGPU enables rendering to the canvas. After creation, it needs configuration to link with a device. Multiple canvases can share the same device, and they can be reconfigured as necessary. It supplies a texture for rendering, and there are several resource types in WebGPU. First, we have the GPU buffer. It defines the size and its usage. It can be used from uniforms, vertices, indices, and general data. Next is the GPU texture. It designates dimensions as 1D, 2D, or 3D, along with size, maps, samples, formats, and usage. Then there is a GPU texture view. It is a subset of a texture used for sampling or as rendering targets. You can specify its use as a cube map, array texture, and more. The GPU sampler is also important. It dictates the texture's filtering and wrapping behavior. It's crucial to note that all these resources maintain a fixed shape post-creation. However, their content can be modified. The device comes with a default GPU queue. Currently, it's the only queue available for use. However, future API versions might offer more options. This queue is essential for submitting commands to the GPU. Additionally, it features useful helper functions. These assist in writing to buffers and textures, and they are the simplest method to update the content of these resources. It's highly recommended to make use of them. To record GPU commands, start by creating GPU command encoder from your device. This allows you to transfer data between buffers and textures. You can then initiate render or compute passes. Once you're done, it generates the CPU command buffer. Remember, command buffer remains inactive until they are queued. And once a command buffer is submitted, it can't be reused. Passes play a significant role in GPU operations. A render pass can utilize GPU render pipelines. It binds to vertex or index buffers, issues draw calls, and write to one or multiple textures. On the other hand, a compute pass taps into GPU compute pipelines. It's responsible for issuing dispatch calls. It's essential to note that when a pass is active, you can't record other command types. However, both render and compute passes have capability to set bind groups. Initially, a render pass requires you to provide details about its attachments. This includes the output destination and methods to load and save them. Here, the clearing of data types take place. It's also where you establish multi-sample results, ensuring accuracy at the pass conclusion. Now let's explore the main high-level differences. When beginning to work with graphic APIs, the first step is to initialize the main object for interaction. This process has some differences between WebGL and WebGPU, which can cause some issues in both systems. In WebGL, this object is called context and represents the interface for drawing on an HTML5 canvas element. Obtaining this context is quite easy, but it's important to note that it's tied to a specific canvas. This means that if you need to render on multiple canvases, you will need multiple contexts. Yeah. WebGPU introduces a new concept called device. The device represents a GPU abstraction that you will interact with. The initialization process is a bit more complex than in WebGL, but it provides more flexibility. One advantage of this model is that one device can render on multiple canvases or even none. This provides additional flexibility, allowing for one device to control rendering on multiple windows or contexts. Buffer management in both APIs looks the same. However, in WebGPU, once a buffer is created, its size and destination are fixed. It's also worth noting that don't bind the desired buffer. Instead, it simply passed as an argument. This approach can be found throughout the whole API. For shaders, the big change is that WebGL uses glsl and WebGPU uses a new shader language called wgsl. It's designed to cross-compile nicely to the various backends' preferred shader variants. Note that in wgsl, the fragment and vertex shaders can be part of the same shader as long as they have different function names. This can be very convenient. WebGL and WebGPU are two distinct methods for managing and organizing the graphic pipeline. In WebGL, the primary emphasis is on the shader program, which is combined vertex and fragment shaders to determine how vertices are transformed and how each pixel is colored. To create a program in WebGL, you need to follow simple steps. Just write and compile a shader code for source code for shaders, attach the compiled shaders to the program and then link them, activate the program before rendering, and transmit data to activated program. That's all, yeah? This process provides flexible control over graphics, but can be complicated and prone to errors, particularly for large and complex projects. When developing graphics for the web, it's essential to have a streamlined and efficient process. And in WebGPU, it's achieved through the use of a pipeline. The pipeline replaces the need for separate programs and includes not only shaders, but also other critical information that's established as state in WebGL. Creating a pipeline in WebGPU may seem more complicated initially, but it offers greater flexibility and modularity. The process involves three key steps. First, you must define the shader by writing and compiling the shader source code, just as you would in WebGL. Second, you create the pipeline by combining the shader and other rendering parameters into a cohesive unit. Finally, you must activate the pipeline before rendering. Compared to WebGL, WebGPU encapsulates more aspects of rendering into a single object. This approach creates a more predictable and error-resistant process. Instead of managing shaders and rendering states separately, everything is combined into one pipeline object. By following these steps, developer can create optimized and efficient graphics for the web with ease. Finally, we get to drawing. Again, WebGPU looks more complex, but that's actually in this case. We are more explicit about setting up render target, whereas WebGL, there is a default one, yeah. But during the actual rendering, WebGPU avoids setting up the vertex attribute layout because that's part of the pipeline. Let's now compare uniforms in WebGL and WebGPU. Uniform variables offer constant data that can be accessed by all shader instances. With basic WebGL, we can set uniform variables directly via API calls. However, this approach is straightforward, but necessitates multiple API calls for each uniform variable. With the advent of WebGL 2, developers are now able to group uniform variables into buffers, a highly efficient alternative to using separate uniform shaders. And by consolidating different uniforms into a larger structure using uniform buffers, all uniform data can be transmitted to the GPU at once, leading to reduced API calls and superior performance. In this case, in the case of WebGL 2, subsets of a large uniform buffers can be bound through a special API call known as bind buffer range. Similarly, in WebGPU, dynamic uniform buffers offsets are utilized for the same purpose. allowing the passing of a list of assets when invoking the setBindGroup API. This level of flexibility and optimization has made uniform buffers a valuable tool for developers looking to optimize their WebGL and WebGPU projects. A better method is available through WebGPU. Instead of supporting individual uniform variables, work is exclusively done through uniform buffers. Loading data in one large block is preferred by modern GPUs instead of many small ones, rather than recreating and rebinding small buffers each time. Creating one large buffer is using different part width for different row calls can significantly increase performance. While WebGL is more imperative, resetting global state with each call and striving to be as simple as possible, WebGPU aims to be more object-oriented and focused on resource reuse, which leads to efficiency. Although transitioning from WebGL to WebGPU may seem difficult due to differences in methods, starting with a transition to WebGL 2 as an immediate step can simplify our work. Transitioning from WebGL to WebGPU involves modifying both API and shaders. The wgsl specification facilitates a seamless and intuitive transition while ensuring optimal efficiency and performance for contemporary GPUs. I have an example shader for texture that uses glsl and wgsl. glsl serves as a connection between WebGPU and the native APIs, although wgsl appears to be more wordy than glsl, the format is still recognizable. The following tables display a comparison between the basic and matrix data types found in glsl and wgsl. Moving from glsl to wgsl indicates a preference for the more stringent typing and clear specification of data sizes, resulting in better code legibility and lower chance to make mistake. The meta declaring structures has been altered with the addition of explicit syntax for declaring fields in wgsl structures. This highlights the need for improved clarity and simplification of data structures and shaders. By altering the syntax of function in wgsl, it promotes a unified approach to declarations and return values, which results in more consistent and predictable code. If you're working with wgsl, you'll notice that some of the built-in glsl functions have different names or have been replaced. This is actually helpful because it simplifies the function names and make them more intuitive. This will make it easier for developers who are familiar with the graphic APIs to transition to wgsl. If you're planning to convert your WebGL projects to WebGPU, there are a lot of tools available that can automate the process of converting glsl to wgsl, and one such tool is Naga. It's a Rust library that can be used to convert glsl to wgsl, and best of all, it can be even used right from your browser with the help of WebAssembly. Now let's talk about some differences in conventions between WebGL and WebGPU. Specifically, we will go over the disparities in textures, viewport, and clip spaces. When you migrate, you may come across an unexpected issue where view images are flipped. This is a common problem for those who have moved applications from OpenGL to Direct2D. In OpenGL and WebGL, images are usually loaded so that the first pixel is on the bottom left corner. However, many developers load images starting from the top left corner, which results in flipped images. Direct2D and Metal systems, on the other hand, use the upper left corner as a start point for textures. The developers of WebGPU have decided to follow this practice since it's appeared to be a more straightforward approach for most developers. If your WebGL code selects pixels from the frame buffer, it's important to keep in mind that WebGPU uses a different coordinate system. To adjust for this, you may need to apply a straightforward y equal 1 minus y operation to correct the coordinates. If a developer encounters a problem where objects are disappearing or being clipped too soon, it may be due to differences in the depth domain. WebGL and WebGPU have different definitions of the depth range of the clip space. While WebGL uses a range from -1 to 1, WebGPU uses a range from 0 to 1, which is similar to other graphics APIs like Direct2D, Metal, and Vulkan. This definition was made based on advantages of using the range from 0 to 1 that were discovered while working with our graphics APIs. The projection matrix is primarily responsible for transforming the position of your model into a clip space. One useful way to make adjustments to your code is to ensure that the projection matrix generates outputs ranging from 0 to 1. This can be achieved by implementing certain functions available in libraries like glmatrix, such as the perspective CO function. Other matrix operations also offer comparable functions that you can utilize. In the event you're working with an existing matrix projection and that can be modified, there's still a solution. You can transform the projection matrix to fit the 0 to 1 range by applying another matrix that modifies the range before the projection matrix. This pre-multiplication technique can be an effective way to adjust the range of your projection matrix to fit your needs. Now let's discuss some tips and tricks of working with WebGPU. First of all, of course, minimize the number of pipelines you use. The more pipelines you use, the more state switching you have, and the less performance it results. It may be not trivial, depending on where your assets come from. Creating a pipeline and then immediately using it works, but don't do it. Just create functions, return immediately, and it start work on a different thread. When you use it, the queue execution needs to wait for pending pipeline creation to finish. This causes a significant jank. Make sure you leave some time between create and first use. Or even better, use the create pipeline async variants. The promise resolves when the pipeline is ready to use without any stalling. Render bundles are pre-recorded, partial, reusable render passes. They can contain most rendering commands, except for things like setting the viewport. They can be replayed as part of an actual render process later on. Render bundles can be executed alongside regular render process commands. The render pass state is reset to defaults before and after every bundle execution, primarily for reducing JavaScript overheat or dropping. So GPU performance is the same either way. So transitioning to WebGPU is more than just switching graphic APIs. It is a step towards the future of web graphics, combining successful features and practices from various graphics APIs. This migrations requires thorough understanding of technical and philosophical changes, but the benefits are really significant. So thank you for your attention, and I hope you enjoy the conference. See you.